Hi everybody! So today we're going to take a look at one of the in-person optical mineralogy demonstrations that I do. This demonstration uses a large homemade polariscope along with a sample of cullet glass and a sample of quartz with large windows cut perpendicular to the C crystallographic axis. Here's the experimental setup for our quartz versus glass demonstration. We've got our samples of quartz and cullet glass. There is an LED light board, which is the diffuse light source for our polariscope, and then we have two pieces of linear polarizer that in this case are framed just to make them a bit easier to handle. What is usually absent from my in-person demonstrations is the ring stand, and in that case that's just here to hold the camera so that we get a nice view of what's going on with our polariscope. Alright, so let's try out some of the demonstrations here. These are all best done in a dim room. All the optical phenomena are just a bit easier to spot when there's less incident light bouncing around and possibly messing with what we're seeing. Right now we're just looking down onto that LED light board which is turned on, and now I'm going to bring in our first piece of linear polarizer. The light from our LED light board is vibrating in all sorts of different directions. But after that light passes through our linear polarizer, it's only going to be vibrating in one plane. For today with this polariscope setup, our light is vibrating in an east-west direction. So the light we are viewing is plane polarized, and this is the setup of our polariscope we want to use if we want to explore the phenomenon of pleochroism in our mineral samples. But in order to explore a whole host of other optical phenomena, we're going to need a second polarizer, and we're going to want to orient this upper polarizer so that its vibrational direction is perpendicular to our first. Our first polarizer allowed light to pass that was vibrating in an east-west vibrational direction. This upper polarizer is only allowing light to pass in a north-south vibrational direction. Our polarizers are crossed polarizers, and so very little light is making it to us. That is, unless we put a mineral sample in between our polarizers, and then the structure of our mineral can do interesting things to light. If you want to learn more about linear polarizers or polariscopes, check out the educational videos Snellius Minerals Linear Polarizers or Snellius Minerals DIY Polariscope. Let's bring in our cullet glass sample and examine it with plane polarized light to start. We won't need our upper polarizer for this first experiment, and we're now viewing how plane polarized light interacts with our cullet glass specimen. The phenomenon of pleochroism would occur as a change in color as I rotate our specimen here in a bunch of different viewing directions. And you'll notice for our glass, not really much of anything happens. Our glass specimen does not display pleochroism, and the behavior it displays is the same in all directions through our glass sample. Let's take a look at our quartz crystal now and see if it does anything interesting in plane polarized light. Right now we're looking down the C crystallographic axis of our quartz, and as we rotate the quartz you'll notice that nothing really is happening. Well, that's boring. But that's just because the C crystallographic axis isn't the right direction through our quartz crystal in order to view pleochroism. We need to be looking along the plane of the A-axis in order to view the maximum pleochroism for our quartz. When we change our view to looking along the plane of the A crystallographic axis, you'll notice the quartz changes color as we rotate. It goes from like a pale straw yellow to a much darker yellow. Now this is a pretty mild demonstration of pleochroism, but part of that is because of the color saturation of our crystal. If our crystal were darker, the pleochroism would actually show up a bit better as well. The important point from this demonstration is that our crystal can behave differently in different directions. That's because of our crystal's structure. Its orderly internal arrangement of atoms that repeats over and over again with the same symmetry. This allows our crystal to behave differently in different directions. A lack of long-range structure in our glass means that glass won't be able to behave differently in different directions. Glass is isotropic, the same in all directions, and crystals can be anisotropic, that is, different in different directions. Let's continue on and bring in our upper polarizer now to take a look at our glass and our quartz with crossed polarizers. Right off the bat, you'll notice our quartz is letting a whole bunch of light through and also has some interesting rainbow effects going on. The glass primarily stays dark, but does have a couple bands of light running through it. Let's check out what happens when we rotate our cullet glass specimen with the crossed polarizers and take a couple different views through our sample. Our glass lets a little bit of light through, and we can also see these interesting waves of sort of light and dark as we rotate the glass. And what that is actually is stress in our glass sample. A perfectly annealed piece of glass wouldn't have any of this really going on. It would just stay pretty much dark with crossed polarizers. But this is just a piece of cullet glass, so this is sort of like a leftover scrap from glass making. And this demonstrates one of the important industrial uses of polariscopes is to check on the stress of glass and plastic products in order to figure out how things might fail or break. Check out how different the behavior of our quartz crystal is, though, compared to the glass that we just looked at. We're looking down the C crystallographic axis now, and as we rotate the crystal, you'll notice not much changes. However, we do get the transmission of light here and also this bright rainbow pattern, which we'll explore a bit more in detail later. When we reorient the crystal to look down the plane of the A-axis, however, you'll notice a very different behavior. So in this orientation, the crystal is primarily dark, but as we rotate it, it transmits light, and then we can rotate it to go back to darkness. So this is the extinction and transmission of light, and this is once again caused by that quartz crystal structure. And how that quartz crystal structure is aligning with the vibrational directions of our linear polarizers. Let's go back to our original setup looking down the C axis of our quartz crystal. At this point of the demonstration, I usually bring in a converging lens in order to generate something called an interference figure. However, we can actually do the same thing just by bringing our camera close to our crystal, since our camera also has a converging lens in it, and that's what we'll try today. As we bring our camera closer to our quartz crystal, I want to pause for a moment and mention the interesting rainbow-colored triangles that we see. These are Brazil law twins in our quartz crystal, and you can sort of think of them as a structural defect. Now, as we get closer to the area of the crystal without any of these Brazil law twins, you'll see an optic axis interference figure for quartz. This pattern consists of a central circular area of a particular color, surrounded by rings of color extending outward from that circular center area, as well as 4 dark bands known as isogyres. The colors we're seeing here are all very pastel, and that actually has to do with the thickness of our quartz crystal. Usually people aren't doing this test with a quartz crystal so thick. If we move our camera over some of the other portions of our quartz crystal where we have those Brazil law twins, you'll notice everything gets a little bit odd. Under the right conditions, this would actually be able to generate something known as Aries spiral. However, this particular crystal has just a bit too much going on to do that. Now to examine something that has nothing interesting going on, and if we look at the glass, you'll notice nothing interesting is going on. Back to our quartz crystal, we get an interesting optic axis interference figure, and back to the glass, we get nada. And that's pretty much the big theme of today. Because our quartz crystal has a crystalline structure, it can do all sorts of interesting things to light. When viewed in plain polarized light, our quartz crystal can demonstrate pleochroism, whereas our glass cannot. When viewed with crossed polarizers, our quartz can demonstrate the extinction and transmission of light, whereas our glass just lets a little bit of light through under these viewing conditions due to stress remaining in the glass. And when viewed close up with a converging lens, our glass doesn't do much of anything. However, our quartz generates an interesting optic axis interference figure. There's a whole bunch more to learn about quartz and to also delve into with these experiments. The video Snellius Minerals Quartz Slice is a good place to start to learn more. Small versions of the quartz slice can be found at the eBay store Snellius Minerals, and I'm always happy to make custom things for folks trying to do similar demonstrations. If you have any questions or comments for me, please reach out at the email snelliusminerals@gmail.com. Here are the references I used in the creation of today's video. Thanks again for watching, and have a great day.